Welcome everyone. I'm Jagnesh. I'm the statistics trainer. Okay, so before we start, let me introduce myself. So I'm a senior data scientist who's having 10 plus years of experience in machine learning. So I'm currently working with an organization who's mostly concentrate on deep learning activities. For example, image recognition, natural language processing. So that's my main duty. Okay, so before we start the session, we can talk about why statistics is important in terms of machine learning. Okay, so but obviously you can have a question that why do we need statistics basically? Okay, so how it basically impacts machine learning, because that is very important. Okay, so I can tell you, statistics is the backbone of machine learning. Okay, so every equation derived from statistics. Okay, so basically, machine learning is full of mathematics, right? So every equations, every steps derived from the mathematics. So obviously, not only statistics, we should know about differential equations. Okay, so we should know about little integration. We should know about probability theory, measure theory. So why not? So this is how it goes. So we should know about each and everything. Okay, so but more than anything, statistics is the primary. Okay, so I can tell you a simple. I start with simple example why statistics are primary. Then we go with each and everything. Okay, so let me open Notepad. Okay, so you all heard about Bernoulli distribution, right? Okay, so basically we'll see Bernoulli distribution next week. Okay, there's something called binomial distribution that basically came from Bernoulli distribution. But in this session, I'll just tell you like how statistics, how we derive the machine learning equation from statistics. Okay, so we have something called linear regression. Okay, so and anyway, we'll talk about this in detail. Okay, so the linear regression is basically, okay, it's the very basic algorithms in terms of machine learning. So what linear regression will do, okay, so for example, I have input like this, number of experience. Okay, so I'll just zoom this, number of experience. Okay, this is one of the field, and then age, and then okay, team, and then skills. Okay, so and then salary. So now this is my input data. Okay, so now assume that you have a data like this. Okay, so you have a data called number of experience, age, and then skills, and then salary. Okay, so now your job is to, okay, so now we talk about the linear regression, right? So you have number of experience, age, skills, and salary. Okay, so this is the input field basically. Okay, so we call that as a features, number of experience, age, skills, and salary. Okay, so the point is, okay, so this is my training data. So I have to train this. Okay, and finally I have to predict the salary. Okay. I have to predict the salary. Okay, so based on these features. Okay, so assume that I got a training data. Okay, this is my training data. Okay, so assume I got some 1,000 numbers of training data. Okay, 1,000 training data. Okay, training data basically consists of all this: number of experience, age, skills, and salary. Means we will say features and targets. Okay, so we call input as a feature. Okay, or an input variable. Okay, so anything is fine. But if you go to the research paper, basically everyone talks about features instead of input variables. Okay, so our features are number of experience, age, and skills. And our target is salary. Okay, so now the point is I have 1,000 training data, okay, which consists of number of experience, age, skills, and salary. Okay, so now I have to predict the salary based on the features. Okay, so this is basically a linear regression problem because I can say the salary is a continuous variable. Means the continuous is we'll anyway discuss about continuous and discrete variables. Okay, the continuous variable. So this is a regression problem. I'll apply linear regression. Okay, so to futures and target, I'll apply linear regression. Okay, and then I'll create a model and save a model. Okay, after that, what I'll do, I'll deploy this model in cloud or wherever you want. Okay, but just for topic purpose, okay, so we can say that we can deploy the model into cloud. Okay, and someone have all these features. For example, they go into the market, they get a resume. Okay, so from the resume, they extracted all those informations, number of experience, age, and skills, and then they'll hit the model that is available in cloud with these features. Okay, so I took some resume. From the resume of a particular person, I get number of experience, age, skills, and then I'll hit the model that is deployed in cloud. Okay, and then I'll get the target as the output, which is the salary. Okay, so this is basically linear regression, right? So if I want to, I have enough data available, so I just want to predict the pattern, and finally I just want to get the target based on the features. Okay, so now let's go little technically. Okay, so basically linear regression works with objective functions. So we call there is objective function or cost function or loss function or objective function. Okay, so generally, people use all these three terms. Okay, so generally it is loss, but sometimes you heard cost, sometimes you heard objective. It depends on the trainer. It depends on the material. Okay, so the objective function is basically x, the input, into log of. I'm sorry, this is basically y. So y is the target. So I can say target actual output into log of one minus t. Okay, so let's not think about this formula. Okay, let's not worry about how we derive this formula because anyway, in the further classes we would talk about this thing. Okay, so but right now we have to understand where this formula derived from because that is very important. Okay, so we know that the objective functions or cost function or loss function is this for linear regression, and basically linear regression works based on these objective functions. But where we derive this? How we come to know that this formula will work well. Okay, so that's where our question comes, right? So basically we have to go back to statistics, okay, to understand this. So this is basically derived from Bernoulli distribution. Okay, so if you see a machine learning, okay, so if you see any algorithms, okay, it starts with linear regression, logistic regression, support vector machines, or decision trees, random forests, okay, they do have objective function because everything works with objective functions. Okay, so we'll find the error based on the objective functions, and then we'll tune we'll fine tune in such a way that we can reduce the error. Okay, so we have basically two processes in machine learning algorithms. We'll have objective functions, and then we'll have the fine tuning algorithms. So that's basically every machine learning algorithms has. Okay, so if you understand this concept, okay, so if I go to any machine learning algorithms or something comes new in the market, okay, that basically has two in that. Okay, so one is objective function, another is the fine tuning part. Okay, so in terms of linear regression, the objective function came from the Bernoulli distribution, and then the fine tuning function is the gradient descent algorithms. So within gradient descent, there are multiple flavors. Anyway, so I can say that the backbone for this objective and fine-tune algorithms are statistics. So anything should come from statistics. So obviously, if you are good in statistics, obviously, you can easily relate this. Okay. So that's why, we see statistics before we see data analytics as well as machine learning. So now let us go to the presentation. Okay. So, and obviously we know that studied statistics in school or colleges, but now when it comes to industry, it is a little different. So we'll go with each and everything. Okay. So how we can start with statistics. So you say that I'm a fresher in case of statistics, how I can start with. Okay. So basically now when I see a particular variable, okay, so assume that, I get a variable called salary. Okay. So how I can get the intuition from the variable salary? Okay, so that's the basic question, right? Okay, so assume that you have some Excel. Okay, and you have something called salary. So in that you do have some variables like 10,000, 20,000, 30,000. Okay, these are like that. You have multiple fields. Okay, so now when you see the salary, okay, so how you can get the insights? What kind of you can get insights using statistics? So basically, I can come up with 3 factors called mean, okay, or median, okay, variance, and standard deviation. Okay, so everyone knows that we do have mean, variance, and standard deviation, but using that, how I can get the data insights. Okay, so how this can help me to understand this data. Okay, so first of all, I need to understand, okay, there are 2 things in terms of stat. So I have get the input like this, okay, the salary, this 10,000, 20,000, 30,000. Okay, so how I can get the insights, okay, based on this statistic variables, okay, so which is mean, variance, and standard deviation. Okay, so basically, you know one thing, that if you just want to understand the population, obviously we cannot calculate each and every one of the population, because that's basically a very hard concept. So what we used to do, we'll go to each and every region. For example, if you want to calculate the population in case of India, okay, so basically we cannot ask each and every people, right? So we'll take a sample. So from Karnataka, we'll take some sample. From Himachal Pradesh, we'll take some sample. From Assam, we'll take some sample. And then finally, we come up with some algorithms, and then we calculate the populations. So obviously, when it comes to statistics, we do have 2 things. One is population, another is sample. Okay, the population is, okay, the population is basically everything. Means, for example, I need to take some survey. Okay, so if and I have to take survey from 1,000 people. That's the total population. Okay, so 1,000 people who is working in some industry. Okay, so in the whole world, only 1,000 people are available. Okay, so what I'll do, I'll go to each and every people and I'll take the survey. That has nothing but the population. Okay, but instead I cannot reach the 1,000 people. I don't have a resource like that. Okay, so I can reach only 50 people. Okay, but I'll try to find insights from the 50 people itself. Okay, so that's my question. So we call that as a sample. Okay, so if I go to each and every people and get the input, that is nothing but a population. But obviously in the real world application, obviously we cannot go to each and every people. So I'll try to minimize my requirements. I'll reach only 50 people. I'll get the input from them, and based on that, I'll derive something that is equal to population, or that is very close to population. Okay, so obviously that's my important intuition. Okay, so we call that as a sample. Okay, so this is very important. Okay, so in the later part, we talk about population and sample a lot. Okay, I guess you understand population and sample very well. Okay, so population is nothing but a total inputs. Sample is from the population. Okay, so from 1,000, we got only 50 people. From the 50 people, we got the input. That's nothing but sample inputs. Okay, so now anyway, we do have 2 inputs, right? So how I can understand the sample is good from the population? Okay, so for that, the mean, variance, and standard deviation will help me. Okay, so for example, I get the inputs from 1,000 people. Okay, and I calculated standard deviation is 1. Okay, standard deviation is nothing but, okay, so I have 1000 inputs. From each and every input, what is the deviation? For example, if you go to salary, okay, the first salary is 10,000, second salary is 20,000, third salary is 30,000. Then here the standard deviation is 10,000, because from the first input to the second input, I have 10,000 difference, and from the third to second input, I have 10,000 difference again. So that's nothing but a standard deviation. Okay, so like that. Okay, so you collect the samples, you collect the inputs from population. Okay, and you find that the population standard deviation is 1, and you collect the samples from the same population, but you choose only 50 people. Okay, so when you calculate the standard deviation, assume that is 6. Okay, now, so we have to think about it. Okay, so the standard deviation in case of sample is 6, the standard deviation in case of population is 1. Okay, so you collect another sample from 60 people. Okay, so assume that one guy collected samples from 50, another guy, so we call as a sample 1. Okay, another guy get the input from another 60, okay, which is sample 2. So here, when you find the standard deviation, it is again 1. Okay, so now we can, by using standard deviation, we can say that sample 2 is good rather than the sample 1, because the sample 2 standard deviation is better than the sample 1 standard deviation, as well as the main point is the samples 2 standard deviation is equal to the population standard deviation. So obviously we can say that we can go ahead with the sample 2. So like that, we'll see mean and variance. Okay, so whenever we get the input, we'll calculate the standard deviation, mean and variance, and we calculate with the real world example. If it matches with the real world example, then our sample is correct. Okay, so by using standard deviation, mean and variance, we can calculate this kind of things. This is one example. Like that, we have a lot of, we can come up with a lot of intuitions. Okay, okay. So now I got a question that how you're assuming standard deviation on what basis? Okay, so let us first calculate let us first understand the formula of standard deviation, mean and variance. Okay, so then we can go ahead with all those questions. I'm sorry. Like anyway, I'll come back to this question later. Okay, so first we'll define mean, variance, and standard deviation. Then we can come back to this question. So let's go to the PPT. Okay. Okay. So the mean is basically, this is the formula. Okay. So as I said that we do have sample population mean and sample mean. Okay. This is the sample mean. So here you can say that sample arithmetic mean. So mathematically we denote as a x bar. Okay. That's basically 1 by n sigma I is equal to 1 to n x of I. So assume that this is x of I. Okay. This is x of 1, x of 2, x of 3. Okay. So here I is equal to 3 because I have 3 inputs. Okay. So then the mean is x1 plus x2 plus x3 divided by 3, which is the total number of inputs. So that is nothing but a mean. Okay. So when you calculate the mean here, it basically, 30,000, 50,000, 60,000 divided by 3 is equal to 20,000. So the mean salary is 20,000. Means, most of the population from the sample get a 20,000 salary. Okay. Some people, individually, some people will get a 1 lakh salary. Okay. But this is again an outlier. Okay. So the mean salary is 20,000. So that's basically mean tell us. Okay. So we do have mean, but why we do have median? Okay. Because mean and median will average basically. Okay. So we do have mean. Why we need median? Okay. So the mean is not very sensitive to outliers. For example, if another person was getting 1 crore salary or 10 lakh salary, okay, that is possible in the real world. If he's a specialist in some field, or virtual reality, some high skill, and he get 10 lakh salary. So now if I include this guy in the formula, I'll get a high deviation, isn't it? So, it may go 80,000 or something like that. But this is the mean changes because of this guy. Okay. But other people are really getting low salary. Okay. So when I include this guy into the mean, this will obviously distract my entire calculation. Okay, so we call this the outliers. Okay, so when you have outliers in your input, when you find outliers in your input, it is better to go with median. So the median formula is, median basically, list everything in order, starts from 10,000, 20,000, 30,000 and till 10 lakhs. Okay, for example, here we have 5 inputs, which is 10,000, 20,000, 30,000, 1 lakh and 10 lakh. Okay, so what I'll do basically, I'll take the middle number here. So 1, 2, 3, 4, 5. Totally we have 5 inputs. Okay, so I'll select the middle one, which is nothing but a median. Okay, so if I have the 6 input variables, yeah.
So you said outline to the high value.
The outliers, yes.
Outliers, sorry.
So outliers.
Outliers can also be referred to the low value. Suppose somebody is taking salary 1,000 rupees.
Exactly, yes. We do have both extreme. You're correct, yes.
Okay.
Okay, so this is basically outlier. So means it is basically lying. So that's why we call this an outlier. This is a very important term in machine learning, guys. So the outlier is very important. Okay, so now when I have the 6 inputs, okay, so I basically, take the third and fourth one. I'll take the average from this. 25,000 plus 30,000 divided by 2 is nothing but a median. Okay, so the difference between mean and median is, okay, so basically mean and median will do the same job. It basically take the average from the input, but when you have outliers, it basically you can go with median rather than mean. Okay, then what is variance basically? Variance is, now this is your input, you calculate the mean value. Okay, so now you have to understand how my each and every input will differ from the mean value. Okay, for example, my first input is 10,000. Okay, divide means subtracted by mean gives me 10,000. Okay, so then I can say that, okay, so in the market, okay, people are getting 20,000 salary. When I find this kind of requirements, means for example, you're recruiting particular people, okay, for some jobs, maybe some support jobs, okay, and you're giving 10,000 salary, okay, but people, same to him in the market getting 20,000 salary. Okay, so basically that is the mean salary. So if I calculate my salary with the mean salary, then I'll get the variance. So variance basically tells me that, okay, how my input is, changing with the mean. For example, if I get a 10 lakh salary, think about the outlier who's getting 10 lakh salary, then the variance is totally big. Okay, so from this I can say that if the variance is 0, it's well and good, because it is exactly matching with the mean. That's a major intention. Okay, so but as of now, think about the calculation, mathematical calculation. Okay, so variance is nothing but the actual value, the actual input subtracted from the mean. Okay, and the standard deviation is simple, very simple. It's basically the square root of variance. Okay, the square root of variance is nothing but standard deviation. But here we saw that, right? The standard deviation is, okay, so the first input and second input have the deviation of 10,000. Second input and the third input have the deviation of 5,000. Third input and fourth input have the deviation of 5,000. Like that, okay, you calculate each and everything. And then when you take the average, you'll get the standard deviation from the sample. Okay, so from the standard deviation, I can say that, okay, so, that's what we have seen. From the population, I get a standard deviation of 1. From the sample 1, I get the standard deviation of 6. Then I can tell that, my sample is not correct. Okay, I took a sample who's basically, having outliers as well. Okay, but my sample 2 has the standard deviation of 1. This is basically good. Okay, so this is exactly matching with the population. So this is what the basic concept. So whenever you get a variable, whenever you get an input, either in terms of from MySQL, from a SQL file system, or from Excel, okay, you take every inputs like salary, okay, you calculate standard deviation, mean, variance, median, everything, okay, and then you can see that how my input is. Okay, this is basically help us like how statistically this is correct, not correct, something like that. Okay, so when you talk about variable, there are 2 kinds of variables. Okay, so the one is categorical variable, another is continuous variable, means not continuous variable. numeric variables. Okay, so you understand that what numeric variable is. So if something with numbers, that's nothing but a numeric variable. So the salary is a numeric variable because it's a number. Okay, so instead of a number, I have something like this: low salary, medium salary, high salary. Instead of numbers, I categorize with characters. This is nothing but a categorical variable. Okay, so anything starts with number is nothing but a numerical variable. Anything starts with character, that's a categorical variable. Okay, so now tell me, like if it is a number, obviously we can calculate mean, median, variance. If it is a character, obviously we cannot calculate all this. Okay, so obviously categorical variable is a very different sense. We'll talk about categorical variables a lot, but as of now, we do have two variables. One is numeric variables and other is categorical variable. Okay, so within categorical variable, we do have two kind of things. Okay, the one is nominal variable, another is ordinal variable. Okay, so in the PPT, you do have all those things. Okay, nominal variable, ordinal variable, but right now we'll see practical. Okay, so in the categorical, basically, if anything starts, so if anything is with characters, then we call that as a categorical variable. Okay, categorical variable. Okay, within categorical variable, okay, we have two kinds of categorical variable: ordinal and nominal. Okay, so from the word itself, we can understand. Okay, nominal doesn't have any meaning. Okay, means male, female, like that. Okay, is it having any order? Basically, mathematically, it doesn't tell anything. It's a normal variable. It's a nominal variable. But if I mention low, medium, high, this basically have some order. Low means a very less. Medium means between low and high. High means very high. So this has some mathematical notation, right? We call that as an ordinal variable. Okay, so very simple. Whenever the variable starts with character, having character in it, that's nothing but a categorical variable. Within categorical, we have nominal and ordinal. Okay, so nominal means it doesn't have any mathematical meaning. Ordinal means it has meaning. Simple. Okay, so like that, we do have numerical variables, or we can simply say numeric variables. Okay, so numeric variables also have types. Okay, so one is discrete, another is continuous. Okay, so discrete is, for example, let's talk about salary. Okay, so salary is basically continuous, because when I group this, okay, can I get any group? Obviously I cannot, because I cannot predict what value I can get next. Anything from 10,000 to 10 lakhs or even 1 crore, it basically, I can get any value. Some people will get 10,050 as a salary. Who knows about it? Okay, so obviously I cannot predict that my salary is within this limit. Okay, so that's nothing but the continuous variable. Okay, and discrete is, take a very simple example. Okay, for example, from which state he is. Okay, 0, 1 is Arizona, and 2 is California, something like this. Okay, so that US basically US has 50 states, and every state has the number. Okay, this is a numerical number 1, 2 till 50. Okay, so now you can tell easily that if my variable is state and it is numeric, obviously it should be between 1 to 50. Okay, so obviously you cannot get any value that is more than 50 or less than 1. Okay, you cannot get any floating point value like 1.5, 2.5, something like that. Okay, so you'll get any value that is between 1 to 50. That is nothing but discrete. Okay, so that's basically in the PPT we discussed about it. So we do have variables, qualitative and quantitative. I call it as a numeric and categorical. Within categorical, we have nominal and ordinal. Within numeric, we have discrete and continuous. And we discussed about mean, median, mode, standard deviations, everything. Okay. Now, okay, so now I get some inputs. Okay, basically this is number of experience. I'm sorry, I'm writing in paint. So okay, yes, this is number of experience in the x-axis, and y-axis is salary. Okay, so now I take assume that I get 50 samples. Okay, so 50 sample having number of experience as well as salary. Okay, so assume that the first data having experience of 1 and getting 10,000 salary. Okay, the first sample is having number of experience as well as salary. Okay, like that I have 50 samples. Okay, so now you take this first sample. Okay, the number of experience is 1 year here. The number of means the salary is 10,000. Okay, here the first point comes. We call that as a first sample. So like that, when you pick up 50 samples and plot it in a scatter plot, we get something like this. Okay, when you plot it, you basically get like this. And you all see this. This is nothing but a bell curve or a normally distributed curve. Okay, so now I get another curve, another plot, something like this. Okay, this is basically non-linear curve. So we call this as of now we know forgot normal distributions, forgot about the distributions. Okay, so think whether it is linear, non-linear. This is basically linear. This is basically non-linear. Okay, so now in terms of machine learning algorithms handle linear input very well, but not a non-linear input. That's why we go into deep learning. Because you understand, right? So since machine learning is not very suitable for linear problems, non-linear problems, we go into deep learning. So obviously the essence is, so here the essence is, the important point is, okay, so if I apply machine learning algorithms for a non-linear input, yes, it's well and good. But if I having non-linear inputs, means I don't have linear inputs within me, I do have a non-linear inputs, but I have to apply the machine learning algorithms. What I can do, linear in the sense, so you can if you plot the x-axis and y-axis, you'll get a curve like this. Okay, otherwise, if you put a formula like y is equal to 2x plus 1. Okay, so basically if something behaves, for example, x is your input, so x is number of experience, salary is y. Okay, so put 10,000. Okay, so this is basically a formula, right? So x is number of experience, y is the salary. Okay, so when you give number of experience as 1, I'll just replace 1 here. 2 into 1 is equal to 2. 2 plus 10,000 is 10,002. So that's nothing but my salary. So when something, okay, behaves with this, behaves well with this formula, I can basically derive a single formula. Okay, so within that, whenever you give me the experience, I'll come up with a salary. If something well suited with this approach, then we call that as a linear variable. Okay, or a linear problem. Okay, so but here, can I come up with any function? Yes, I can come up with a function, but that is a very critical then. Very critical. Okay, that is nothing but a non-linear. Okay, so in terms of graphical content, if anything normally distributed, okay, anything have something like this, you can see that this is a single curve. It has a mean. Okay, so it has a standard deviation, everything. Okay, so I can calculate basically between one standard deviation, to another standard deviation, how many values stacked together. I can basically, okay. So I think you have a you do have a problem to understand linear and non-linear. But right now, okay, so don't think much about linear and non-linear. Okay, if something platted like this, that is nothing but a linear. Okay, if something platted like this, that's nothing but non-linear. Okay, so it is it's a sample plot. Okay, so I can basically derive this within a very simple function. Then that's basically a linear problem. If I doesn't come up with something like this, then that's basically a non-linear problem. Okay, don't confuse a lot anyway, because this is very early to talk about linear, non-linear, but we'll come again.
Hi. So do you mean that the machine learning can be applicable only for linear examples or linear situations?
That's the basic understanding. See, we do have something called support vector machine that is well suitable for non-linear problem, but we do one simple setup, which is we use kernels instead of features. So we collect the features and we convert everything into kernels, and then we apply into the support vector. We apply support vector machine. So what I mean to say, if I have a non-linear input, okay, if I want to apply into machine learning algorithms, what I'll do, I'll convert my non-linear input into linear input using some function.
Maybe you'll have to have more samples, I believe.
More samples. So even though I get more samples, some if you think about the critical variable, that is basically non-linear, right? If you go to the real-time variable in the world, obviously, we may get linear as well as non-linear. We cannot predict basically. Yes. Okay. So, but why it should be linear, non-linear? When we discuss about gradient descent algorithm, obviously we'll discuss, why we should consider only linear, non-linear. Okay, because if it is linear, we can mathematically it is mathematically highly approachable. If it is non-linear, it is very difficult.
Correct.
Okay. So obviously
something like driverless car in US compared to driverless car in India, that would be linear and non-linear. In India,
exactly. That might be one example as well. Yes, in US, yes, they do have certain rules. We can call that as a linear problem, but in India, obviously, we cannot consider that as a linear problem. Yes, that's one example. But as of now, don't think that why it should only applicable to linear, non-linear, because that's how the mathematics derived basically. We have a gradient descent algorithm that is well suitable for linear than the non-linear problem. Okay, we'll discuss about that one by one. Why when we discuss about gradient descent, we'll discuss about that. Okay, but right now, just trust me, just believe on me. Okay, so we do have the machine learning part. Okay, the machine learning is well suitable for linear than the non-linear. But if you ask me a question, okay, I have a non-linear problem, but I want to apply machine learning algorithms, then you have to convert all the non-linear input into linear input. Then only you can apply the machine learning algorithms. The one example is support vector machine. Okay, so obviously when we discuss about support vector machines, we'll discuss that one. Okay, but this is too early to go into depth. Okay, so right now we are concentrating in statistics. Okay, so but what I'm saying is, so why I take this point basically. Okay, the point is, okay, so now I get a non-linear input. Okay, something like this. Okay, now I have to apply machine learning algorithms. So that to apply something into machine learning algorithms, I have to convert my input into a linear input. Okay, so but I got a non-linear input. Now I have to convert non-linear into linear. How I can do this? You can basically apply statistics. Okay, so what you can do, you can use some functions. Okay, so for example, you get a non-linear input. You have to convert this into linear input. Okay, so you have x basically, this is non-linear input. What you can do, you can apply some functions. Like this. Okay, so just this is basically a trial and error. Okay, so you'll have some input that is non-linear. Okay, then you convert that into log of x. Okay, you plot this, and this might be linear, or you can do exponential of x. Okay, so that the exponential function or monotonic function, either it could be decreasing or increasing. So you apply this to a variable called x, and then it'll just check whether it is a linear input, non-linear input. So we have to understand logarithmic function, exponential function, all those things. Okay, so now that's why the statistics are very important. Okay, so when you think about the problem, okay, you come up with some assumptions. So the assumption is simple. Okay, so when it is a non-linear problem, then obviously that is not suitable for machine learning algorithms. Then we have to convert the non-linear into a linear problem. Okay, that's the first step. For that, we need statistics. Okay, so we successfully converted a non-linear into a linear input. Now we can go for the machine learning algorithms. So when you create a pipeline, practically, because I worked in multiple projects. Okay, so because for the last 10 years I worked with machine learning projects. So from my experience, I can say that. Okay, so if I get 60 days for a project, then I can build algorithms, evaluation, everything within 1 week. Because now we can use scikit-learn, or we can use TensorFlow. We can easily do this, right? A programmer can do this basically. Okay, so what is the major part? The major part is to identify this kind of things. Okay, we go to each and every variable. We'll see how the standard deviation, variance, and mean. Do we need more sample, or the sample given are enough? Okay, so whether each and every variable are linear, non-linear. Okay, and then so we have to drive all this. That's very important. Okay. Okay, so basically I can say the formula of mean, median, mode, and standard deviation, but formula wouldn't work out. Okay, so that's why I tell some practical scenario. Okay, so from the practical scenario, I derive all this. Okay. Okay, so now we discuss about another thing as well. Okay, so there's a concept called measures of dispersion. Okay, so you can understand now. So what it tells, how to spread out the distribution. That is how variable the data are. Okay, so basically what they're trying to say. Okay, take this example. How this is distributed. Okay, so that's basically the measure of dispersion. So okay, what is the standard deviation? Okay, what is the lowest value and what is the highest value? Okay, so when you find the difference between the lowest value and highest value, that is nothing but a range. Okay, so you can basically measure the dispersion, right? So you can measure how this distribution is. Okay, so to measure this distribution, basically you need the high value, low value, standard deviations, variance, and everything. Okay, so that's basically the measures of dispersion. So I mean to say, like, we do have a lot of examples. So if you calculate range, variance, standard deviation, mean, mode, then obviously you can understand this kind of theories. Okay, so range, you know that when you have the high value or minimum value and the maximum value, the difference between the minimum value and the maximum value is range. Okay, so in one example we talked about salary, right? So we got the minimum salary is 10,000, maximum salary is 10 lakh. The difference between 10 lakhs and 10,000 is basically huge. So obviously, it is not a good sample. Okay, so from the range, you can understand that whether the sample is good or not. Okay, so that's basically range tell us. Okay, and then you guys know what is the formula for variance and standard deviation. Okay, the variance is nothing but each and every value of an input variable. So this I denotes 1 to n. Okay, so the x1, x2, something like that, minus this is mean. Okay, divided by n minus 1. So here the point is why we divide from n minus 1 and not divided as n. Okay, so we do have two variants. One is population variance, another is sample variance. Okay, so the population variance is, we'll hide this minus 1. We won't divide by n minus 1. Instead, we divide by n. Okay, but to penalize, okay, as of now, right now, I'm not explaining this. I'll give you as a homework. Okay, just see why sample variants are divided by n minus 1 rather than n. Okay, we'll discuss about next week. Okay, so why this is. Okay, so just go through this. Just go through Wikipedia. Just go through Khan Academy. Okay, so why it is divided by n minus 1? Why sample variants are divided by n minus 1 rather than n? Okay, so just tell me the difference. I'll explain more in detail next week. Okay, so standard deviation, you know that the square root of variance is nothing but standard deviation. So when it comes to sample standard deviation, the sample standard deviation is nothing but the square root of sample variance. Okay, so we discussed about population and sample. Okay, so population and sample, mean, median, and standard deviation formula are almost same, rather than this one difference. If it is a population variance, we divide it by n, which is the number of sample. But for sample variance, we divide it by n minus 1, which is again the number of samples. Okay, so you have to understand why we have to minus 1 in the denominator. Okay, so you'll just find the answer. This is very simple. We'll explain next week, because one hidden concepts are there in this. Okay, and we do have the last topic, which is we have Chebyshev's theorem. Okay, so what Chebyshev's theorem? Okay, this again, it will come up with another thing. For example, okay, take this example again. Okay, so here the mean is 5. Assume that the mean is 5. Okay, so assume that we have a salary. Okay, not 5, 50,000, because the salaries we call this a 50,000. So the average salary in a particular sample is 50,000, and the standard deviation is 10,000. Okay, so we call this a 1 standard deviation and a 2 standard deviation. Okay, so every standard deviation, okay, deviated with a value of 10,000. Simple. So this is minus 1, this is minus 2 standard deviation, this is plus 1 standard deviation, and plus 2 standard deviation. Okay, so like that, we'll have multiple standard deviations in the positive as well as negative range. Okay, so now you know this. So you know what standard deviation is, what mean is. Okay, so now someone asked the question. Okay, so you have 1,000 samples. Okay, so out of 1,000 samples, how many samples are lying between 2 standard deviation? Simple. So if anyone asks a question, okay, so I have 1,000 samples. Out of 1,000 samples, how many samples are lying between the 2 standard deviation, which is minus 2 and plus 2, between minus 2 standard deviation and plus 2 standard deviation? How you can calculate this? Okay, so to calculate, you can basically follow Chebyshev's theorem. Okay, so this k is nothing but a standard deviation. It should be greater than 1. Okay, so now the question is, how many samples are lying between 2 standard deviation? So you can apply this formula, 1 minus 1 by 2 square, which is 1 by 4. So which is basically 3 by 4. So 3 by 4 samples are lying between 2 standard deviation. So almost 95% of the samples. I'm sorry, 75% of the samples. Okay, that's nothing but Chebyshev's theorem. Okay, so we discussed about all this. Okay, what is countable number, what is not countable numbers. Okay, so when it is continuous, basically we cannot countable this. It could be anything. Okay, when it is discrete, basically we can count this. Okay, so okay, and then we have laws of expected value and laws of variance. We'll discuss about this. Okay, so what is expected value now? Okay, the expected value is nothing but the average value or the mean value. Okay, for example, this is the formula. You just think about the formula. Okay, so I have a constant value, which is 10,000. The expected value of constant is what? That's the question. Okay, so you apply the same mean formula. Okay, so I have a constant called 5,000. Okay, if it is a constant, we cannot say this is which variable this is. This is not a variable, so I cannot say this is salary. This is, this is simply a constant. So obviously, the mean is nothing but a constant. Okay, that's the formula is saying. When you want to calculate the expected value of a constant, that's nothing but a constant again. Okay, so now you have scenario like this. Okay, a variable plus constant. The expected value of variable, x is a variable and c is a constant. Okay, so assume that c is 5,000 and x is some 10,000 value. Okay, and it has multiple values. So now basically you calculate the mean for this. Okay, because this is a variable. Okay, so basically you can calculate a mean, but for constant there's nothing. So you can rewrite in the formula like this: the expected value of x plus constant. Okay, so now you have something like this. A constant come with this 2 into 10,000, 2 into 20,000, 2 into 30,000. So now what could be the expected value? So that's basically C into E of x. Okay, because when you calculate the mean, you'll take this is a 20,000, this is a 40,000, this is a 60,000. Okay, for that you'll calculate the mean. So obviously the C comes into picture. Okay, so when it comes to variance, you apply the same formula. Okay, what the variance is? Okay, now variance is the difference between the actual value from the mean value. Okay, so now take the same example. We have 5,000. Okay, we have 5,000 as a constant. So what you'll do basically, you'll divide 5,000. You'll subtract the real value with the mean value. So here the mean value is also 5,000. Okay, so 5,000, the actual value, which is constant 5,000, subtracted from the mean value 5,000 is 0 basically. So that's why this formula is same. Okay, so if it is a x plus c, basically when you minus, okay, x plus c minus x minus c, basically this x will drop out. So you'll get only v of x. Okay, so basically when it is come within x, basically this will be square. Okay, so for example, you just try to apply the variance formula. Okay, x hat. This is the variance formula, right? X minus mean whole square. Okay, so when you just replace the value cx instead of x, you'll get this. Okay, see, okay, the laws of expected value are nothing but a mean. Okay, so you know what mean formula is. So the mean formula is, for example, this is the variable x1, x2, and x3. Okay, so the mean value is x1 plus x2 plus x3 divided by 3. Okay, so now we have the constant. Okay, so constant is basically a single value. Okay, so what could be the mean then? Okay, so single value divided by 1 is nothing but c. Okay, so that is what here. Okay, so if we want to calculate the mean for a single value constant, okay, so what I'll get basically a same value, c divided by 1 is c. Okay, so now instead of c, you'll have x plus c. So what you'll do basically, first you'll calculate the mean for x. Okay, so mean of x is expected value of x plus this constant. So that is what they expect. Okay, so the expected value of x plus constant. Okay, so now when it is cx, okay, this is basically c into a of x. Okay, so when you apply the same concepts to law of variance, okay, so you have c. Okay, what is the variance formula? It is this. Okay, so the actual value, the real input minus mean whole square is basically the variance formula. Okay, so the x value is c now. What is the mean value? Okay, so when the mean value is also c for constant. So c minus c is basically 0. So that's what this. Okay, the variance of constant is equal to 0. Okay, so now the variance of x plus c. Okay, let's do this. What is the variance of x plus c? Again, okay, the x plus c whole square minus x plus c whole square. Okay, this is basically x plus c whole square, the real value, minus e of x plus c whole square. Okay, so when you come up with a value, that's nothing but a v of x. Okay, it will basically remove the constant. Okay, so 1 will give plus c, 1 will give minus c, both will cancel out. Okay, so that's why we get v of x. So when you substitute c constant into x, you'll get c square into v of x. Okay, so we'll try it out. So that's what we'll get. So that's what they say here, laws of variance. Okay, so I think it will clear doubt, correct? Okay, so now the last function is probability distribution and probability mass function. Okay, so now I'll simply explain this, then we'll close the session. We'll go with some questions. Okay, so when you're all fine, then we can close the session. Okay, so now you know we have two variables, discrete and continuous variables. Okay, so discrete variables are nothing but I can assume the variable are between this value to this value. For example, between 1 and 50. Okay, those are nothing but discrete variables. Okay, so if continuous variables means I cannot say this could be the value. It could be anything, 0 to infinite, or I can say minus infinite to plus infinite. Okay, so now we took this linear problem and come up with this formula, right? Okay, y is equal to 2x plus 10,000 in one example. Okay, so now this is basically a function. Okay, so I get so many samples. Okay, then I'll plot it like this. I'll come up with a function. Basically, in the x-axis I have number of experience, in the y-axis I have salary. Basically, this will follow some logic. So if I make this plot as a function, I'll get one function. Okay, for both continuous as well as discrete variables. Okay, so if I come up with function for continuous variable, that is nothing but a probability density function. Okay, for discrete variable, that is nothing but a probability mass function. Okay, so simple. Okay, so I get some sample and I just want to make this as a function. Okay, so I basically get two kinds of variable. One is a continuous and another is a discrete. For a continuous variable, if I derive some function, that is nothing but a probability density function. For a discrete variable, if I derive any function, that is nothing but a probability mass function. Simple. Okay. So anyway, we'll discuss about this. We'll discuss about probability density function and probability mass functions in the coming sections. Okay. So the next section, okay, we'll start with every distribution. We'll take the samples, we'll come up with the distributions, and then we'll see what is the probability density function and probability mass function for those distribution. Okay, we'll derive mathematically, and then we'll see how it could be useful. But let us summarize. Okay, so we start with a problem. Okay, so I should, that's how we started. We take one variable called salary. We calculate mean, median, mode, standard deviation, variance. Okay, and then we try to understand how I can, how this can help me. So, we took some examples. Okay, we derive each and everything, like how the continuous variables will behave, how the discrete variables will behave, those kind of things, right? So anyway, in the further section, we'll describe more and more. Okay, so till then,